Right. Okay, spatial temporal databases. Oh, a couple of nigh on self-evident definitions. Temporal database is simply a database that manages the change in attributes through time. Spatiotemporal database manages spatial data through time. What a surprise. Right. Okay, so in the temporal database, we're going to consider some spatial temporal data types. We're going to look at, find the difference between transaction and valid time, look at some spatiotemporal data models, and then temporal relationships. As you'll discover, things get thinner and thinner probably as we go down the list in the amount that I can say about these things. Okay, so temporal data types, unsurprisingly, Postgres and most relational databases support a variety of spatial data types. Come on. Come on. Get some power. Okay. Right, so a variety of different types of temporal data types. So obviously sometimes you only have the time of the day. So there's a time data type that just stores time of the day. Date, just the day of the year. A timestamp is a day and a time. A timestamp Z is a day and a time with a time zone. So how far you are offset from UTC. Interval is basically a time period. So you can define a time period. And you can also do a range or series where you have a number of dates basically as a list, as the way I understand it. But, again, from my perspective, this is no good because this is limited to dates because of the number of bytes and things used to store the data in the underlying database system. And the fact that most computer applications are about the present or the recent past or the future, not the deep past, they are limited to 4,713 BC to, so I think we're all right for the future, but it's not so good with the past. Personally, I think some of this future should have been given to the past, but there you go. It was a decision, this was a legacy decision from the 1970s when databases and computer time systems were put together. So the lesson is, if you're dealing with any times that are outside of those ranges, then your standard date time fields are no good. Not any good. So, is that all I had on data types? Well, that is all I've got on data types. I've been looking for, say, geological period data types. I'm sure they exist somewhere, but I can't find them. So, if anybody finds anything for interval times and things like that, then you maybe want then point them in my direction. Personally, I'm working at anything from, most of my data, maybe 100 years, but in theory it could be anything from the present day into maybe 15 million years in the past. I can work at the scale of 1 year with an integer field, basically. So I have the present day as basically 0, or, for most of my stuff, it doesn't really matter where 0 is because I'm dealing in units of 500,000 years, or 100,000 years is kind of my minimum temporal unit. So I can get away with just an integer figure for something like that. That's how I deal with date times. Okay, so you've got these data types. They may not be suitable if you're dealing with deep time. Okay, now this is important. There are two types of database time. There is what we call valid time and what we call transaction time. So a valid time is also world time or cartographic time, and that is normal time, the time at which something happens in the world or is effective in reality. The time you got up this morning, the time you go to bed tonight, the time when you were born, absolute time. And that is inherently part of the data model because you're recording the date in a field, in a row, in a table. Yep. Then there is transaction time. Transaction time is about the database and when the fact was stored in the database. Yep. So this is about updates and changes inside the database rather than in the world. So it records the database state at a particular time, which allows you to reverse your database to say, what was my database state like, say, 18 months ago? This can be really important. It provides traceability. Imagine the case where you've got a legal claim against you and somebody is saying, well, this is the information I was given 18 months ago, and you gave it to me. The company could then, or the organization could then go basically rewind time in their database back, and they could look at the situation as it was 18 months ago and say, well, this is the information we had 18 months ago, and this is why we told you why. So it's very useful for sort of traceability and understanding how your data has changed in time. And that is part of the relational database data model. So relational databases provide tools for managing transaction time, whereas valid time has to be designed as part of your data model for your application. So we start off with transaction time just because it's the easiest. It's the simplest. Okay, so basically time evolves discretely with each transaction. Every time something happens in the database, something is changed in the database, then T is obtained from the system time on the computer. So the computer has a clock inside it, which may be updated from UTC automatically or may not be, but basically the database goes to the computer, says what's the time, gets the time, and stamps the change with that value. You can only update the current state, so you can't go back in time. You're not allowed to go back to T2 and said, well, the change I made from T2 to T3 was in fact incorrect. I want to get rid of that change. You're not allowed to do that. It's inherent to the data model that you can't go back and change things. If the change between T1 and T2 was incorrect, then you should have another change further up the change that changes it back, and probably a note saying why it was changed back so that you've got a record of what was going on and why it was going on. Okay, and then because when we've got this simple chain of events, we can just roll back the time and say, well, roll back my database, take those changes, take them off the system until we get back to the T at time X. Postgres has an extension called temporal tables that supports this for you. So basically, I've never done it myself, but it's meant to be relatively straightforward to set this up. There's a pre-existing data model. It's quite like PostGIS. It's an extension for this kind of stuff. Now, transactions are effectively instant. You change a data value in your database, it changes instantly. But records change over longer or exist over periods of time. So transaction time can be implemented at lots of different levels in a database. So you could record every change to every attribute, or you could record changes to a row, or indeed change, or in this case, in respect to spatial data at the level of a geometry. So here's an example of transaction time with just a sort of employee database. They seem to be very popular for database examples. So employee 10, 20,000, started work in this position on the 9th of September 1993, worked in the job until October 94. We have one stamp for when this row started, was valid. So this is our transaction time scale. So this record was put in on this date. There should be some sort of time scale here. That time may not exactly be that start time. Maybe the record was put in the month before because the employee was started, you're employed by somebody, you're offered a job, and then you've got a month or 3 months before you take up the job. So the employee record may have existed in the database from a period before the actual start of the employment. Yep. So without that recording this date. This start date is not the same as the transaction date. That's what I'm saying. This is the date that the person did the job. And we have two starts. They started, that record went into this record when this row went into the database at this time, then it became obsolete at this time. And you can see it was replaced. They had a massive pay rise. They did well, didn't they? They've almost doubled their wages. And from that period, we can see that we could put a link. So, for example, if a person couldn't have two jobs, then we could put a constraint that no time period, or certainly between the actual job fields, that these dates couldn't overlap. But here, you've got this row is valid between this time, and then this row is valid between this time. Yep. So this is the time that the database changes have actually occurred within the database. And we just have open-ending values where things haven't stopped. Okay. So basically you put stamps on things, you record the changes, relatively straightforward. Valid time. So valid time is when something occurs in the real world. And as I say, it's part of the domain model, which means you have to implement it as a database designer when you're implementing your data model. And that there's a whole variety of data models exist that you could use to implement time in a database. Somebody organise it. Order of some of these slides is a bit complicated. Okay. So let's first of all, before we decide, look at how we record things in the database, let's just have a little visit again to a bit of a closer detail at how entities change in time. And I'm going to sort of skip over this relatively straightforward. So this is from a paper here in 2005, and it's showing the various ways in which a geometry might change through time. So these are geometries, and we can see that, and this, remember the list that I had earlier, this is basically a graphical representations of those lists, so we can see the relationships a bit more closely. So we've got the things coming into existence, disappearing from existence, things that they just stay the same. So this is a typology of what could change, which involves things not changing as well. Okay, so things might stay the same, they can expand, contract, deform, change shape, and they may move, or they may rotate or something like this. So these sorts of changes, so our database model would need to potentially incorporate some or all of these changes. Now, whether you need to record all of these changes or not, it depends on what your needs are of your application. Okay. So obviously appearance and disappearance is relatively straightforward, but how you deal with expansion, contraction or displacement is another matter. For example, with displacement, this geometry is exactly the same, it's just that its position has changed in the geographical space. You could have one polygon that, say, has two centroids, one centroid at time t and one at time t2. Or you could have two polygons, one for each time period. So you can see that there's alternative ways in which you could model the same change in a database. The relationships between entities might also change in time. So one thing becomes replaced by another thing. Their orderings in space may change. Things may, you may get diffusion processes whereby things physically move or infect other close by entities, so it may create new entities. So this may be like a dispersal of a population. Here's a population of, I don't know, frogs in a pond, and here they've dispersed and have occupied some neighbouring ponds as well. Or that's more like, is that reproduction or production? I must say, so one thing is, I think this is reproducing versions of itself, and this is producing new things that are sort of emerged from that one. We've also got things like transmission, so this would be an example of infection here. So this person has the cold, people are getting the cold. And then we've got the thing that actual entities themselves, individual things, can merge and coalesce through time. So our data model You may or may not need to either record these types of processes, either record it in the data structure or provide a data structure that allows us to analytically generate these kinds of patterns so that we can see whether these kinds of patterns exist in the data, relationships these kinds of relationships exist in the data. Paquette provides a classification of spatiotemporal data models. So these are ways in the computer that we can store temporal information. And I can't say I totally agree with this classification. Like most classifications of these kinds of things, you can do it in different ways. You can interpret it in different ways. But this is the way they do it. Location-based models, which are basically temporal snapshots. Entity-based models, which store changes through time. And then they call time-based models, which actually store a topology of time. So we're going to run through these quickly. Location-based models. These are to be honest, these are probably 99% of time-related applications use location-based models, and the rest of them are more theoretical, although they do have applications. So sequential snapshots, dead easy. A layer is specified for each time period. So, for example, you may have periodic surveys once a year, once every decade. So the census is an example. Census is a periodic survey. Or it may be that you output from some sort of simulation model. For a climate simulation model, you're outputting a layer, say the temperature, average temperature over a year or a month or something like that. So you get a stack of layers at different time periods. And in this case, time is an attribute of a layer. So it's not an attribute of an entity within a layer. These may be vector, they may be raster, but each layer has a time associated with it. Okay? If we want to know what's happening between our time periods, so say these are annual ones, and we want to know what's happening halfway between one and the other, we have to have some kind of interpolation algorithm in space or in time to estimate the conditions between our surveys. Importantly, this model has no inherent model, or that the change in the entities is not encoded in the data model. So what do I mean by that exactly? Well, okay. Here we have, if we take maybe this location here, at this point in time, it's, well, let's take this one here. It was yellow. What yellow is, who cares? It was within the yellow zone. Then it's not in the yellow zone. Then it's, well, maybe in the yellow zone again, whatever. But the only way we can tell whether there's been a change is by comparing the layers. Yep, we have to actually do an analysis, a query between the layers to understand what's changed. The change is not inherently encoded. There is nothing in this square that's telling me that in the next time period it's changing, and in the previous one it was the same, yeah? I only get that information by analysing the different layers. There's a lot of data redundancy. If nothing changes, we've duplicated the data, but nothing has changed. So we've got data redundancy, yeah? Each layer has lots of information which is exactly the same. So we're storing redundant data. Change is not inherent in the model, that's just repeating itself again. It's also very difficult to impose any kind of temporal constraints on these models. So for example, if there must be at least 2 years of being yellow in each cell, how would you tell? It's only through analysis could you find that, say, this cell had only existed as yellow for 1 year. Okay, so it's difficult to put constraints on. But it is by probably one of the most used temporal models. As I say, those layers could be in vector or raster. Doesn't really matter. This is a sort of the space the 3D, 4D space-time raster model is a kind of, it's just a sort of an extension of that layer-based model. In fact, to me, they're exactly the same, but I think it's good to just contrast them. So in this case, this is basically this is a raster model. And basically, it's instead of, so in a raster model, you know, you divide the world into equal shaped squares, usually squares. It could be rectangles, usually squares. This is taking it into instead of having squares, we're having cubes or four-dimensional cubes. You've got to get your head around multiple dimensions here. So we could have three-dimensional voxels. So a three-dimensional voxel, so instead of a square, it's a cube. And that cube may be georeferenced in x, y, and t being time. So a standard map, changing through time, we could have a stack of layers with x, y, and t coordinates for each. So vertically, this sort of block of grid square, or block of blocks, cube of cubes, so to speak. As we go higher in the stack, that's changing in time. Now that's exactly the same as the previous model, but there is one difference, and that is that t is almost always the same between each layer. Just like the size of a raster cell is the same in space, the sign of a temporal voxel cell will have the same temporal unit. So this might be, in this case, this is years, I believe. You can extend this model if you had three dimensions. You can stack four-dimensional dot cells into a four-dimensional cube. Okay, so you've got x, y, z. So your dot cells, which anything above a 3D cube is called a dot cell. A voxel for 3 and then a dot cell. So a 5-dimensional or a 6-dimensional cube will be called a dot cell too. We'll get on to. I was doing a later lecture the other day, and I got, interestingly, got to the point where I was looking about multi-dimensional spaces of multi-dimensional spaces. So that's something to look forward to in a future lecture. Anyway, we've got these x, y, z, t coordinates. Each cell is just located in 4 dimensions, and that's how we can do elevation as well. So here is an example of a 4-dimensional space-time raster displayed in 3 dimensions, with a 4th dimension of being displayed in color. So this is a digital terrain model, and how a digital terrain model has changed through time. Let's see whether I can understand this off the top. So the colors are giving us the year, and I think let's see, how do we interpret this? So the color is the year. The vertical dimension is, to be honest, I think I understood that once upon a time. Anyway, you go and look at that website. That will tell you what it is. Then you'll hopefully be understood. I think that's a good lesson in that these things can be really complicated to understand and to visualize. Yeah, I know this is something about a DTM through time, but now I'm looking at it, my brain is not fully understanding what's going on. Look at that reference, I'll tell you what it is. But you understand the principle. It's the multi-dimensional, 4-dimensional cubes. Okay, so we've got this problem of redundancy, remember? If nothing's changed between the layers, we're recording numbers that we don't need to record. Yep. Standard, remember, run length encoding for compressing spatial rasters and things like that. So we can compress raster for 4-dimensional or 3-dimensional raster data. We can use a compression techniques to reduce the amount of our data volume and to get rid of redundancy in our data set. So in this case, we've got a raster, and what we store is a list of changes for each raster cell. So we're getting outside of your standard GIS models here. We're in sort of, these things are, there are software that implements these things, but this is not in ArcGIS or anything like that. So in that case, in this case, you store a base state, which is your initial grid values. So maybe if we're talking about something like the index of life or whatever it was called, So we start in 1970 where that starts, and we have values for each cells. And then we only store another value for that cell if there's a change in a particular time period. So basically we have a grid, and then we have a sort of a chain of events associated with each grid cell. And that means we don't have any, we get rid of the data redundancy, we compress our data files so that they're much smaller. Timestamps. Okay, so that's a timestamps provide us another model. So in this case, the time is stored as an attribute of vector objects in a layer. So this is a model that's only really applicable to vector data, not to raster data. And that's very simple. That's just a time field in a table. And then we can record when events occur, single timestamp, or the duration, the start and stop, the beginning and end events of various events. And then you can produce maps for particular time periods by simply querying the field in the layer. So you can have, all right, so if you're dealing with time, you maybe have layers with individual time periods timestamps on layers. You may have time as voxel doxel models. You may potentially have this type of model. I've never used one in my life, but you may well have time here as well as timestamps within tables. So time is spread across your data model. That's the story. That's what I'm saying to you potentially. Time is not in one place. There is not one place where time may exist. Time may exist in various locations across your data model. All right, entity-based models. So an entity-based model explicitly encodes entity change through time. And it's an extension of the vector topology model. Topology model being, can polygons overlap? Do lines have to split and end when they cross another line? All that kind of stuff. And generally what these things is they do is they're like the time, transaction time, in that they track amendments from some initial point in time. So this is one model that's called the base state plus amendments model. So in this example, a poor choice of colours, absolutely. They look all right when they're on the screen, and then you display them up on the projector and it all goes wrong. Okay, they're not very clear. We're looking at rural and urban environments, two land use classes. We're starting off with our database. We've got 4 time periods. We start off with entirely entirely rural environment, and we're looking at urban expansion. So at time period 2, maybe this is every decade, this part has now become rural. So all we store is the polygon with a timestamp for when this became rural. Urban, yeah. Okay, the base state, so if we want at time 2, we basically take this and overlay it onto this and apply the changes. T3, a bit more urban expansion. T4, some more urban expansion again. And then when we translate that into a map, when we want a time period, what we do is simply start at the base step and move forward applying these changes until we get to the right time period that we want. Yep, very straightforward, reasonably straightforward. Okay, this is good. Gives us an explicit model of change. We know what, we can track a polygon through time. It's efficient as only changes are stored. And we can implement temporal constraints on these relatively straightforwardly. We can say that, for example, you can't overlay urban with more urban. That's meaningless, or it's not adding any information. So if this polygon covered some of this area of polygon, we could make sure that that was a constraint in our model, that we wouldn't allow a second conversion of urban to urban, because that's not meaningful. But it is a complex data model that requires all these changes to be tracked, And as the data model grows and grows and grows, time goes on, more and more edits are added on, and processing gets slower and slower and slower. So it's not perfect. Here's another model. This is the space-time composite model. In this case, you have one data layer, so one layer, and what you do is basically have lots of geometries within your layer that are recording this sequential change. Okay, so at time 1, we've got this area. Time 2, these two urban areas or U areas come in, and we can see this polygon is changing the values in this section of this I1 here. So if we want to know the time at T2, we have to go from the polygon at T1, and then we subtract the bit that exists at T2, etc., etc. Okay. So the history of individual geometries is stored as one geometry to many records in a time relationship. Okay, so if we want to know what happens in here, this area here, if we want to know what's happened in here, we have to basically, the state at this point here in a particular time, then we have to get the time stamps for each of the polygons, then run through the sequence, get them into sequence to see what the condition at the time that we're interested in. So in this case, change is added to the base state layer all the time. Now there's a real problem with this one, in that every time something changes, you're cutting your layer into smaller and smaller units. So eventually you end up with these tiny fragmented layers that have to be reconstructed through their attributes. And I've tried to do this, and it is a real pain to do. You also, I hasten to add, need to know completely what's going on within that area to be able to do this. Again, it's a complex data model, and you trying to edit changes that have happened in the past, and then propagating those changes into the future changes are, not surprisingly, quite complex. This data model is used. This is one of the data models that actually is used, and it's used by the historical, what used to be called the GB Historical Database. It seems to now sell itself under a vision of Britain through time. Has Nigel shown you this? It's, yeah, he might well have mentioned it. So it's a project that's run down at Portsmouth University, or it's now has been at Portsmouth for about 15 years. And basically it's taking all the old census data, so that the areas, the enumeration areas and the statistical areas for the census have changed through time. So if you want to look at historical demographic change over long periods of time, then you have to deal with the changes in the administrative area boundaries. And this is a database of those changes in administrative boundaries. And because those administrative boundaries can't overlap and there can't be gaps between them, they need a space-time topological model to maintain the integrity of their data in their database. It's not exactly a very exciting picture, but basically you can see that they break it down. So they're looking at polygons, and they've got, this is based on an old ArcInfo model that predates you lot by a lot and even predates me by a bit. But basically you've got start and stop dates. So this is a topological model in which the polygons are built from lines, yep? So rather than having timestamps associated with the polygons, you have timestamps associated with the lines, and then you recreate the lines to generate the polygons from the lines for the particular time when the lines are valid. Yeah. Okay, good. That was clear. I like that one. Right, okay. 4D space-time geometries. All right, okay, so in this case, what we do is we store the entity is stored as a single geometry, so a vector geometry with x, y, z, t, particularly x, y, z, t coordinates. Chances are you don't have the z. And then these are sort of stored within this, or visualized within what we call a space-time cube. Space-time cube is simply a cube in which one of the dimensions is time and two of the dimensions is space. So if we have a spatial point in a space-time cube, it traces a line through time. If we're a spatial line in space, we trace a plane through space and time. Yeah? Okay. Think this is here we are, we're all at college. Here, there's your homes. You got up this morning, you hung about in the house. Did whatever you do in the house in the morning, then off you came to college. This is your trajectory in space and time. You're all here for a while and then you all go wherever you go at the end of the day. So this is sort of tracing the paths of individuals in space and time. Now if that, instead of points, we were talking about something like a river moves in time, but it exists as a line. If you imagine a line that you then move through this space-time, it would produce a curtain of riveriness, or whatever we want to call it, in space and time. Okay, polygons in space create 3D solids in space-time. 3D solids trace a four-dimensional solid in four-dimensional space-time. Yeah, it makes your head hurt. So this is a data model that is often used for visualization because it allows you to plot these diagrams, these lines. You generate these lines in space and time. You can plot them. They're great for visualization. It's not so great as a database model, potentially for sort of storing and certainly not for maintaining data integrity. So that's your space-time cube. Time-based models, I hadn't even thought about this till I read this Perkett paper the other day. Basically, you have a special line. So not only do you register your data in space in your spatial layers, you also reference these objects along a specific timeline in your database. So rather than getting at time through the entities in your spatial database, what you do is if you want a time period, because they're already referenced on a timeline, you go to the timeline, grab the section of the timeline with all the pointers to the data objects on them, and that gives you really quick, rapid access to the objects associated with that time period. So if you're providing an index in time, basically, which gives you rapid access to the data stored in your relational models, in your data layers, wherever that time is within your domain model. Right. Temporal relationships. These are relatively simple. You can, as I say, within certain database models, you can implement these constraints, or these are simply the relationships that you query. So, for example, does A become before B? Does it meet B in time? Does A stop and B start? Do they overlap in each time? Is one embedded within the other one? So these are the types of queries that you maybe want to undertake between objects, items in time. Also, there is an equivalent not only of overlay, that's overlay in time, but there's also potential for distance in time. So what's the distance between A finishing and B starting, obviously. Now, distance, of course, in this case, we've got 4 different distance measurements that we could make, so we've got to be clear about whether we're measuring the distance. The time between A and B, is it the time between A ending, B starting, A, between the start or end of those various things. So you've got different options there for measuring time distance. Right, quickly, time in ArcGIS. Transaction time, it has a system called versioning, which is a base state plus amendments model. that tracks these additions and deletions to tables. Transaction time in GIS is quite important for certain things. These things that are called long transactions, which is, so for example, imagine we're going to revamp the Kingston Town Centre and we create a new alternate world. We're going to branch time into two possible futures. Then we can, one of those futures has a certain type of urban redevelopment or something like that. Another one has an alternative model. So what we can do with the transaction time is we can split our entire database into two sort of temporal streams, one of which we then put our amendments in, one of which we perhaps keep as the same, the present day, and then when we've actually perhaps decided that we're actually implement the works down in town, then these long transactions are merged back together to create a single representation of what actually happened. Okay, versions must be reconciled. Have a look at this. There's your link, have a look at that. Options for world time in ArcGIS. Okay, you've got your time slider. I hope you've all seen the time slider now. It's a great thing, the time slider. There's also, so for time in a vector field, you can use the time slider. You can use also, there's a tracking analyst server. I'll explain that in a moment. You can take rasters, stacks of rasters, or rasters for different time periods, stack them in a raster catalog or a mosaic table. I think you can do either one. I do raster catalogs. And then you can use the time slider. So that's time associated with a raster layer. You put them into this raster catalog stack, and then you use the time slider to slide through those raster layers. Just you can use the time slider to slide through the time fields in a vector table. Voxels, they have the space-time pattern toolbox supports space-time voxels that are come in a format called netcdf. Read that again, Wayne. And then for 3D geometries using Z for time, you can visualize in ArcScene, ArcGlobe. Okay, really quick time slider. You know this. This is size of male bush crickets in southern France. Not that you care, but year on year. So I went out to the year, I sampled these bush crickets of different years up in the Pyrenees. Here we are, this is the French Pyrenees here. And I've got a sample, so on a year by year basis, so I could look at the size of the crickets that we measured in 2003, 2004, 2005. Yeah, very straightforward. Tracking analyst, well, what's tracking analyst? It's one of these ArcGIS extensions. It's particularly to do with, what a surprise, tracking data, GPS tracks, anything that's a line, basically lines with time stamps along them. And it supports things like additional visualization tools in the layer symbologies, and also the ability to put clock charts and things like this. So remember, cycles in time are particular things happening at particular times of day, dates of the month, etc., etc. What is the cycle? So this allows you to look at cycles. So it's got a whole variety of tools for visualizing, analyzing track-based data. They also have an extension called Tracking Server, which is all to do with real-time GIS tracking of vehicles for things like delivery vehicles and stuff like that, which involves fleet management, sensor networks. So you've got GPS in your truck, so you know where they are. You maybe got, this is used by emergency response vehicles and to manage fleets of delivery vehicles, yodel trucks and things like this. Space Time Pattern Toolbox. I'm looking forward to somebody playing around with this. This is a relatively new addition to ArcGIS, and it's to do with summarizing point data with a date field into a space-time cube. Basically, you're gathering up all your points and you're counting how many fit into each of the bins in your space-time cube. And then it supports various visualization tools to explore these space-time cubes. The data is required to be in what's called NetCDF format, which is a multi-dimensional spatial data format that's, it's used quite a bit, particularly if you're maybe satellite imagery sometimes comes, if you've got stacks of satellite imagery for different time periods or have different bands, sometimes it comes in NetCDF format. So space button pine box. Then ArcScene, you can do visualizations like this. So this is tennis players, yeah. Federer, Matthew, I don't know, it's people banging balls about on courts, I don't know. So in this case, they've got their position on the court through the game, and this is how they move across the court in space-time. So these lines are these three-dimensional space-time lines. This is what I do. This is my stuff. So this is me doing, in ArcGlobe, doing 4D space-time vectors. This is the tree of mammal species, all the 4,000 species of mammals that exist today. Got the range maps of where the species live on the planet today. Got the evolutionary tree of these 4,000 species. I take the evolutionary tree, put the tips of the trees with the species onto basically the polygons where the species exist today. Then we do some arithmetic and locate the sort of ancestral species nodes in the tree back through time. So this is some of the stuff I've been doing over my life. You can see the mass endemism in Central Africa. You can see the relative low number of species in North Africa, unsurprisingly. Interestingly, the nodes over the oceans are much deeper than the ones over the land, as we'd expect, because the species have diversified as the oceans have spread apart, etc., etc. Right, time has many aspects that an application might need to implement in the data model. So what of the first load of sort of hand-waving pretty pictures, which ones of those are relevant to your domain is going to vary. For most applications of time, they're not going to matter, because you're just dealing with sort of present day, relatively recent time. But if you're dealing with archaeological time, geological time, perceptual time, things may be different. Most temporal GIS data models are really kind of space plus time. So basically you get these people just stick timestamps onto things, and then rather than using the more complicated topologic models that we saw, the base state plus changes models, those are unusual. So most people don't use these advanced spatiotemporal models. They just add timestamps to things, which is fine because 99% of the time that's all you need. Real time is spread across, so if you've got a diverse database with heterogeneous data from different sources, the time information is distributed throughout your domain model. So you might have time associated with individual features within a layer. You might have them associated with whole layers. You may have it associated with some sort of voxel model. You may have data in a 3D space-time vector coordinates. My life is full of these things. I have all these different data formats, or this temporal data associated with layers, with individual objects, with models, with trees, and then there's uncertainty on the time, these timestamps as well. It's complicated stuff. And then there's these various tools for exploring and querying the space-time data. We've only really seen a very few of those, just the ones in ArcGIS. There are many others available in particularly exploratory data analysis tools that are available. Some of them, quite a lot of them are free, so have a look at that. Any questions? Appreciate it's not the easiest of things to get your head round. There's the references there. Have a read. The Phuket paper's very good. It's very readable, actually. I'd recommend that. Okay.